look at now are the equations for velocity and acceleration of a simple harmonic oscillator, and we'll find those equations by thinking about the equation for position. So for position, x of t is equal to a, the amplitude, that's the maximum value that x can take on, times cosine of omega, the angular frequency, times time, plus the phase constant phi naught. Right here seems a pretty good place to put in a reminder about our units. Omega was in the units of radians per second, so our argument here is in the units of radians. Your calculator has to be in radians mode. And radians per second is sometimes just called seconds to the minus 1. Okay, so now that note is made. So we have our equation for position. Let's find our equation for velocity. So we'll remember that velocity is the derivative of position with respect to time. So velocity as a function of time is the time derivative of position. So we have to do the derivative of this equation. That's going to give us the velocity equation. So we're doing d by dt of a times cosine of omega t plus phi naught. So in our derivative, the a comes outside, a times the derivative of cosine omega t plus phi naught. The derivative of cosine is minus sine with the same argument. Then we have to finish our chain rule by doing the derivative of the argument. So the derivative of omega t is omega, and the derivative of phi naught is 0 because that's a constant. So this gives us the result that the equation for velocity is minus a times omega times sine omega t plus phi naught. So there's our equation for velocity of our simple harmonic oscillator. If we were going to graph it, we would recognize that the velocity is also a sinusoid. It goes as sine. If our position started at the amplitude, if our phase constant were 0, velocity is a negative sign. Sine normally starts at 0 and goes up. Because it's negative sign, it's going to start at 0 and go down. So if we're going to plot our velocity as a function of time, it would look like this. It has exactly the same period because it has exactly the same angular frequency. So now let's also do our acceleration. So we remembered that velocity was the derivative of position. Acceleration is the derivative of velocity. So acceleration as a function of time is equal to d by dt of the velocity as a function of time. So we've got d by dt of minus a omega sine omega t plus phi naught. Take our minus a omega outside because they're constants. So then we have to do the derivative of sine of omega t plus phi naught. Whoops, I did not need that extra bracket there. And I've got my correction tape here, so we'll just erase that little bit of bracket because we don't need it. Okay, so we've got minus a omega. The derivative of sine is cosine, keeps the same argument. Then we do our chain rule, take the derivative of what's inside. The derivative of omega t plus phi naught is just omega. So now we've got minus a times omega squared times cosine omega t plus phi naught. So there's our equation for the acceleration as a function of time. If we look at this graph, we see that it's a cosine, just like the position graph was a cosine, but this one is a negative cosine. So it's going to look like this one, except it's going to be upside down because it's a negative cosine. So here's our acceleration graph. So next we'll need to ask what are some interesting things about this. So why don't we do that in the next video?